Hi, this video we're gonna talking about strain. Well, what is strain? Strain is talking about deformation. Yeah, in other words, if you have a bar that has been subjected to tension, and what happened to the bar? It's gonna be elongated, right? It's gonna if this is original length is L naught, and now it has become this length, and this L we call L prime, okay? So it has been elongated, and strain is talking about the deformation. How much has been elongated? And here's a little formula for normal strain. Normal strain has a symbol using like epsilon. Epsilon is defined as a change delta in length over original length L naught. So we could rewrite this as the final length L prime minus original length, then divided by original length. So that's our definition for normal strain. Okay. And however, for the shear strain, that's a little bit harder to define. So I will invite you to look at this PowerPoint right here. What I can do is actually going to snip it. Okay. So for shear strain, what we have here is, you notice AB and AC used to be those two lines that originally is perpendicular, and now they have been deformed and they have this final angle as theta prime, no longer 90 degree. So the shear strain definition is going to be equals this. That's the definition for the shear strain. That means pi over 2, 90 degree, but it's in radians. We have to use in radians. Minus theta prime have to be using in radians well. So that means the angle change, right? Used to be pi over 2, now it's theta prime. So the angle change expressed in radians, that's going to be our shear strain. So now let's look at those two equations. One is for the normal strain, epsilon is a change in length divided by the original length. And gamma, that's our shear strain. That's pi over 2 minus the final angle in radians. Now let's look at them. For this shear epsilon, what's the unit for the normal strain? Well, changing length gonna give us in unit using, let's see if we use millimeter. And original length, we use millimeter. What do we have? No unit or unitness. So you realize epsilon, the strain, is unitness. How about shear strain? It's gamma. This gamma pi over 2 is in radians. Theta prime is in radians. So the final unit is in radians. Radians is unitness. So in other words, we conclude no matter what type of strain, either epsilon, normal strain, or gamma, shear strain, the strains are unitness. They have no unit. Okay. All right. So knowing that, we can continue to discover a little bit more about our shear strain. Okay, so let's look at unit shear strain. The first equation is this: pi over 2 minus theta m, theta prime. So you look at this, this used to be pi over 2, 90 degree, and this is going to be our theta prime after deformed. This is our 90 degree. And so this is going to be our gamma, because it's difference between pi over 2 and theta prime. And the gamma is equal to this theta, the angle difference here. Now let's look at, often this deformation is so small, right? So this angle, theta, is very small. You probably learned in calculus, if the angle is so small and this equation works, tangent of this angle is going to be equal to the angle itself, but angle here has to be expressed in radians. Okay. We can prove this. We can do some experiment. Let's see if the angle theta is 1 degree. What's 1 degree in radians? That would be 1 over 180 times pi, right? Let's put in calculator. What's pi over 180? That gives us a very small value, about 0.0174 repeating. Now let's look at what's the tangent of 1 degree. So you can put in your calculator to look at tangent of 1 degree. That also gives us the answer of 0.0174. Okay, so here you see something. If the angle is so small, the tangent of this angle is going to be equal to the angle itself, but the angle have to be expressed in radians. So if that's the situation, we can go back to look at this first expression of gamma, shear strain. Gamma is equal to pi over 2 minus theta prime equal to theta. And this theta, if we're going to look at this right triangle, the tangent of this theta is going to be opposite of adjacent. Opposite would be our delta. Adjacent will be our y. And this angle is so small, this theta is small. Then we already proved it from here. This tangent theta is going to be equal to this theta in radians. And this theta in radians is our shear strain gamma. So we have another expression for our shear strain. So gamma is not only just equal to pi over 2 minus theta prime, it also equal to theta. This theta in radians is basically equal to tangent theta. And that's for this problem will be delta over y. Okay? So that's our second expression for gamma. Which one do we use? Either one work, and choose the one that's the simplest for that particular problem. Okay, so that's the what we have for strain concept. In the next video, we're going to using some examples to apply those formulas and to calculate some of the strains for normal and shear strain. See you next time. Bye now.